Welcome to Ushendra's engineering tutorials. It's something about dual input, unbalanced output, some analysis about dual input and unbalanced output. So how the configuration looks like? It looks like this. Come here. It's two transistors Q, the emitter, and another transistor Q2 with its emitter. Both the emitters are connected, short circuited, and connected to an external resistance RE. And something is connected over here. Hold on. On the other hand, the collector resistance, load resistance RC, and here we have another RC of the same value, so it's RC and plus VCC, connected with the plus VCC over there. And here we have on this side we have minus VEE. We need to have some source, right? Here we have source, input source connected to the base. It's a AC, and one half is grounded, another connected to the base of first transistor B1, and internal resistance of the meter of the source cannot be neglected here. So R in 1, so let it be input source V in 1. Yeah, that's perfect. On the other hand, here even this dual input, right, the name itself says we have two inputs. It's here another source grounded the other side, and we have designated this as V in of 2. Once again, even this is an AC source, we cannot neglect the internal resistance, source resistance R in 2, designated as R in 2, and this is base 2, B2. And what is this? So what if we mean by this unbalanced output? So balanced output, the output is collected across both the collectors, and for an unbalanced output, the output is collected across a single collector. Here it will be from here, in this case V0, output V0, which is equal to, so what are the currents flowing here? This will be IB1, here it will be IE1 here, and it's IE2, and after this node it will be IE1 plus IE2, and IB, here we have IB2 flowing over here, and in that case it's IC1 over here, IC1 flowing in this direction, so IC2 in that direction. So what will be V0 or V0? It will be minus IC2 RC will be our V0. Right? Once again, I am writing for V0 of this for this arrangement. V0 will be equal to, yeah, current is flowing in this direction, so we will be having minus IC2 RC. We're gonna reach, we have to get back to this expression. To reach to that expression we are in search of, right? On the other hand, the transistors, both the transistors are connected in common emitter configuration, and the common emitter configuration, the input is the base and output is the collector. So input current will be the base current and output current will be the collector current. In that case, we have a beta. For every transistor we have alpha and beta. So beta, here even this is important, beta will be equal to the output by input current. It's a current amplification factor, IC by IB, and for a transistor IC will be approximately equal to IE, so IE emitter current, so that will be IC will be approximately equal to emitter current, so that, and IB. So remember this one, that is even yeah, this ratio is correct for beta, right? In the place of IC we can plug in with IE. It's for beta AC current, it's beta AC will be equal to IC upon IB, approximately equal to IE upon IB. Even this is true, guys, we can make use of this one. Even this is true, it is for DC and this for AC, right? So these are the important expressions, and we need to reduce this entire configuration to its AC equivalent. For that, to the derivation which we are in search of, to obtain that derivation. For that case, what we have to do, all the DC sources, this is a DC source that has to be made 0 in the AC equivalent, even this is made 0, and the transistor is short circuited, right? So how to obtain that one? Here the transistor's connection is like it will be like here, it's like this. So here let's draw it. Both the emitters are short circuited, right? Both the emitters are here, both the emitters are short circuited, and we have a common resistance over here. Let it be like a common resistance. What is that? Re, and we don't have supply, it's a DC, so that will be grounded in the AC equivalent. So what current flows through Re? It's a IE1 plus IE2 is the current flowing through the resistance Re. Is that clear? And on either side here, come back to this one, it's in like here. So projecting that one, we have the source resistance V in 1 and grounded over here, and this cannot be neglected. We have to show it, internal resistance of the supply source resistance. And on the other hand, it's a symmetrical, so on the other hand we have to show this one also. So here it's a, what's that? It's a second source V in 2 and grounded, and internal resistance R in 2. And we are done with this one. This is done, and this is done. What about this one? So continuing with this, it's here RC and connected to plus VCC. It's a DC that has to be grounded here. It's plus VCC, and we'll be having IC1 flowing over here. And this one, what about this? Even that we have to show it over here. It's RC and connected to minus VCC, that should be grounded. This contains IC2 and this contains IC1. Now we have the output over here, V0. This is the case, V0, right? In that case, and we have to go ahead. We cannot neglect the dynamic resistance of the emitter junction that comes over here. Dynamic resistance of the emitter junction cannot be neglected. That adds some significant resistance in the circuit. So here that has to be introduced over here in the emitter, RE. Over here also for the second transistor, RE. And where is IB1? Here through the base IB1. Even over here it's a IB2 and I here. In the emitter we have a IE1, also here IE1. After this node it becomes IE1 plus IE2. Yeah, this is perfect. It's a IE1 up to here. It's IE to this side. After this node, both the currents will be added and flowing through RE. Hope it's clear. Output is collected across one of the, hey guys, yeah, unbalanced output. This is the answer. For a balanced output, the output is collected across both the collectors. For unbalanced, the output is collected across one collector with respect to ground. That's my answer, right? And we need some few equations, Thevenin's loop equations, to go in search of that equation which you are in search of. Yeah, here making use of this loop. What is this loop here? This loop, making use of this loop. So this voltage drop will be equal to this drop plus this drop plus this drop. So what will be Vn? Here Vn will be, how to write the expression for Vn? Vn1 will be this drop, Ib1 Rn1, right? Plus going ahead, IE1 Re, IE1 Re plus this one, this current into this. So that will be IE1 Re plus IE2 Re. Okay guys, yeah, it is. So now this IB1, we need the entire expression in terms of emitter currents. It should be either in IE1 or IE2, and this IB1 can be transformed to IE1 making use of this expression. So from here IB1 can be written as IE1 into R in 1 by beta AC, from that one. Okay, and going ahead, it's IE1 RE plus IE1 capital RE, the external, this resistance, plus IE2 RE, and a small transformation over here, taking out IE1 as common from whatever term we have with IE1. So IE1 into R in 1 by beta AC plus RE plus RE. Okay, that's for IE1. We have taken out everything, plus IE2 RE, guys. And in this expression, watching carefully, this entire resistance, this one will be very much larger when compared to this one. So what I mean is, here it's writing over this side, carrying forward to that side. The resistance combination RE plus RE will be very much larger than compared to R in 1 by beta AC. So in that case, this can be neglected and only this can be considered. And simplifying that, what we have is going that side here. I'll be writing over here, don't get confused here. It's V in 1 will be equal to V in 1 will be equal to, guys, IE1 into, we can neglect this one, this can be, this very small when compared to this combination, so we'll consider only that, RE plus RE plus IE2RE, a very important equation for V in 1, right? Now this is expression for the first loop. Follow the same procedure and evaluate the expression for the second loop. That will be leading us to V in the second source. V in 2 will be IE1 RE, the external emitter resistance, plus IE2 that into RE plus RE. This will be the expression for the second loop. You try this, follow the same procedure. And IB2 that will be substituted with this one, and finally that will be leading to this equation. Let it be equation 1 and equation 2. Guys, this could be put it in a matrix form. How to put these two equations in a matrix form? This is how. So here V in 1 and V in 2, that will be equal to what? The current, the resistance is over here, and currents, two currents over here. We have the first current being IE1 upon IE1 over here. The IE1 will be here, and this will be IE2. And these resistances come down as it is. What are those? It's RE plus RE. This comes over here and this comes over here. This is RE, and here it's a RE, and it's a RE plus RE. Now this is the matrix. Making use of Cramer's rule. So what does Cramer's rule help us? Cramer's rule to evaluate IE2. Yeah, you evaluate for IE1, I will evaluate for IE2. So how to evaluate for IE2? IE2 will be given as the fraction, and yeah, this one should be plug in the second component, right? The second term over here. So this should be plug in over here. This comes down as it is. That's yeah, this as it is, RE plus RE, and even this RE comes down as it is, RE it's this one is plugged in over here, changing the color for that you can make it out. So V in 1 and V in 2 over here, and the determinant of this one, and this comes down as it is. What is that as it is? RE plus RE and RE. Here we have RE plus RE here, and the determinant of this one. So this ratio, the determinant of the numerator, the determinant of the denominator of this expression will give our IE2. So what is IE2? Guys, on this side, okay, don't get confused. So IE2 will be equal to here, it's this into this, so RE plus RE into V into RE plus RE into V into minus this one, minus RE into V in 1 upon, so what we have in the denominator, it's RE plus RE whole square minus RE square. So guys, this is for the expression for IE2. This is expression for IE2. And considering this one, which I've written in the beginning itself, the output voltage. So going back to that one, what will be V0? V0 will be equal to minus IC2 RC, which is approximately equal to minus IE2 RC, right? So plugging in the value of IE2 in this expression, what we will be having is V0 will be equal to minus of RC, right? RC and IE2 as it is. And guys, a small transformation over here. What can be written is, okay, no transformation here, so let me go ahead. So IC2 can be plugged in with IE2, and IE2 expression for IE2 I have over here. So that gives me into RE plus RE, okay, into V in 2 minus RE, V in 1, this V in 1 upon, what is that? RE square plus 2 times of RE and RE. Okay, so please make a note the expression for V0 in terms of IE2. This is the expression for V0, and there is a small simplification over here, which is the actual game changer. Please focus. Some assumptions over here. No assumption, the truth, the reality is practically RE will be very much larger when compared to the dynamic resistance of the emitter junction, right? So making this reality fact, we can reduce this one too, guys. V0 will be equal to, guys, taking out V in as common, RC, we have minus RC, that's okay, but taking out negative, which makes us this positive, and what we have is RE into V in, so this will be negative, right? Minus, if this is the case, here RE can be neglected, here this RE can be neglected, we'll be left with RE. So I'll be writing that RE minus RE, V in, this is V in 1 that side, and this is V in 2 upon, in the denominator here, taking out RE as common, we'll be left with, here RE has come out, so it's RE plus twice of external resistance RE over here, right? And yeah guys, that's it. Going ahead, guys, don't mind, I'll be writing over this side. V0 will be equal to RC as it is. So what if we take RE as common from both the terms, RE, we'll be left with V in 1 minus V in 2, okay, it's a V in 1 minus V in 2 upon, what's that? Hey guys, still making use of this one, this reality, if RE is very much larger than this RE, dynamic resistance, this will be even more larger than this, right? So this can be neglected in this term. From here, in this brackets, in this term we can neglect RE. So that will lead us to this dynamic resistance of the emitter junction as it is, RE, that cannot be neglected over in this expression. And in the bracket, we can neglect this one when compared to this one. So that can be written as twice of a RE. So guys, right? So what gets cancelled? Here something gets cancelled, this gets cancelled. And V naught will be equal to RC upon twice of RE. Guys, what is this? V in 1 minus V in 2. Difference of the input voltage. That can be written as VID, difference between the input voltage. So from here, it's a very important statement to be remembered, which should be underlined with red ink, that the output is directly proportional to the difference of the input voltage. Make a note of this one, please. And so that configuration, which configuration? Two transistors connected like this one, back to back. Now this configuration is known as a differential amplifier, because this is the reason. The output is directly proportional to the difference of the two inputs, and so this amplifier configuration is known as a differential amplifier, right? And so going ahead, V naught by V naught by V in difference will be equal to RC by twice of RE, dynamic resistance of the emitter junction, which is equal to the voltage gain, expression for the voltage gain of a dual input unbalanced output configuration of a differential amplifier. Hope you understood each and every step. Nothing is hidden. Hope you understood each and every step in detail. This is a very important expression for the exam, university exam point of view. Hope you understand this one. If you find it useful, please support me with your valuable subscription and a share. Thank you so much. Keep smiling.